Well, as part of our cloud on-ramp effort, we're going behind the scenes on some interesting projects relevant to cloud computing to learn a bit about new opportunities and how researchers are taking advantage of those opportunities. And today I'm talking with Yiyu Ni, a PhD student in seismology at the University of Washington. So Yiyu, thanks for joining us.
Oh, happy to share my experience.
Great. Yeah, I'm looking forward to digging into this. So there's a lot to talk about. So let's start. You've been working on a project you're calling Data Mine, a pretty ambitious endeavor to build a new seismic catalog with machine learning tools with basically our entire archive. And this simply wasn't possible when the archive was on-prem in our data center, but it becomes pretty doable. I mean, you've done it already at this point with the data archive in the cloud. So let's start. Tell me a little bit about the scientific motivation for your project, and what your group is trying to do here.
Great. So I want to start with what we are doing here with Marine Dino at the University of Washington. So we built earthquake catalog, specifically getting interested in the Pacific Northwest region. And back in 2021, when I joined the groups here, the first thing I did over the first quarter, 4 months, I was downloading data, putting data from Iris DMC, which is located just right north in the north gate of Seattle. But it ended up with that for the 100 terabytes of data. We spent like 4 months putting the data to our local server. Then at a point, we started to using machine learning techniques to scan over this continuous data, looking for potential earthquake phase arrivals. And it really being a time-consuming part, accessing this data makes them available to get started for any analysis. So this kind of motivates us when the continuous seismic data at RSDMC or EarthScope becoming available on the Amazon cloud. We figure out, can we scale up our earthquake catalog building workflow so that we can finishing the jobs that usually takes years or tens of years, but now we can, with the cloud computing techniques, we can finish that within 2 or 3 days.
We at EarthScope needed to build things alongside you. This access wasn't ready before you started doing this, and in part, it was good for us to learn, what costs it would incur to us on our side of it, in addition to the costs that a PI has to pay for the processing. So we're excited to talk about this because it means that these things are now possible that weren't possible a very short period of time ago. So let's kind of like paint the picture at a very high level. What was the data workflow for you? So, what data were you accessing? What was the output you were generating? Where did that output go? What method, that kind of stuff.
So generally, the data we're accessing from EarthScope is the continuous mini-seed data. These are data being sent by the regional seismic network, like Pacific Northwest Seismic Network. But there's also some temporary deployment, like, for example, the US array that spans from the West Coast to the East Coast. Everything in mini-seed format. We used to access this data using web services like FDSN web service, data select, but now this data are being uploaded to the Amazon cloud, and so that we have this what we call direct access to the raw infrastructure that stores the data. You can see how data are organized, named, and so that we are just bypassing the intermediate layer through the FDSN web service. So in this cloud-based workflow, what we are trying to do is putting each of this data one day, one station at a time, and we use a machine learning method called FaceNet that is designed and trained for looking for PNS wave arrivals. And the output for our model from the machine learning method is basically this individual PNS waves arrivals, and we write it to a database that records when and where there's a potential PNS wave arrivals. And the workflow is pretty simple, and it's basically what we are doing locally with the on-prem server, but we scaled it to the cloud, so that we're allowed to access directly to the S3 to the cloud storage. Yeah.
So you built your own catalog database then that you had to keep somewhere, right? You had some Amazon storage.
Oh yeah, we're using a Amazon database service called DocumentDB. It's a MongoDB. It's an Amazon version for MongoDB. It's a non-SQL, and it is really good for saving small documents like face pics. We record the arrival times, we record the type of pics, and we record the prediction score, which is pretty important as an output from the FaceNet. So this database is still currently saved on the cloud service, and we're providing some web services that allows general public or anyone to access this data to query for the pics that potentially interested in.
So you mentioned you had been doing this at the local HPC, I assume, at University of Washington there. So the method wasn't new, and you kind of were processing it already. Was there anything you had to change to get either the specific like packages you wanted to use to run, or just to adapt to the file access method? Like how much work did you have to do to take what you had or what you wanted to do and make it work in the cloud setting?
I think the migration by migrating whatever we are doing locally to the cloud, there are two major changes to make it cloud native and scalable. The first thing is the input part, because we seismologists used to use OpsPy and the FDSN web service to request data, but now such web service is not existing on the cloud, and we can directly access to the cloud-based storage. So there is one major change that we made to the workflow is to access to reading the data directly from the cloud storage, and we're not downloading the data. To go further than that, we're not downloading the data from the cloud storage. We're loading it directly to the memory, which means that you don't really need so many local storage on your cloud virtual machine. It can be just computing nodes, and we're loading the mini seed file directly to the cloud. So that's one pretty fancy thing about cloud. And the second thing is that we're improvement or updates to the workflow is to write the pics to a common database. The current size for that document DB is reaching like 4 terabytes or 3 terabytes. So that's pretty major for having a dedicated document or database server if you're running locally. So and that database server is pretty scalable, and we're surprised to find that it takes billions of pics really well with pretty good performance. So I think that's two major updates we made to the workflow to make it scalable and efficient on the cloud.
But otherwise, you were able to use similar tools. You didn't have to find something that was Python to replace what you were. Did you have any of that kind of work to do?
No, we're still keeping in the ecosystem of SciSbench. It's a Python toolbox that allows easy to use APIs for machine learning models like FaceNet, EQ Transformer, and we're keeping within this ecosystem. We even migrating the workflow from local to the cloud. So, yeah.
So the scalability part of it, what did it take to optimize and implement or manage that parallelization? Was there a lot that you had to think about how the tasks should be defined and distributed, or was that pretty much that the software package handled that for you? And I know that I think you worked through some kind of limits that you encountered with our data services staff in getting that to process through. So, what was the work that it took to get that to go?
Well, parallelization and scaling is pretty interesting experience. There are several interesting experiments we made with Earthscope people. So we started with something small that not 1 petabyte, but probably just several gigabytes, to make sure that our workflow is working and there's no major problems or the obvious bugs. Because otherwise, when we launch the 1 petabyte of jobs, we will see all of them failure all at once. That would be a nightmare. We started with something small, and that's also how we define each of these jobs. Each of jobs is very small. It works on like 20 stations, 40 days, and we containerized that workflow as Docker image. And when we launch the jobs, so we can launch like 10,000 of small jobs all at once, at the same time to the cloud, to the Amazon platform. And there was actually account level limitations for the Amazon platform that by default people are allowed to use 4,000 vCPUs all at the same time. 4,000, that still sounds enough for most of the people actually, but we want to see where's the limit. So we request for a quota increase. So, and we're allowed to use 12,000 vCPUs at the same time. That's more than a regular account can access in a HPC cluster or something. And that's 100 times more than what we have on the on-prem server in the department. And we also, with this experiment, we also start with something small, like 1,000 vCPUs at a time, and see how many pressures we're creating for the cloud object storage. We have the Earthscope people monitoring on the back end, watching the request rates getting increased. We are also monitoring how the FDN service are working, if they are working properly, because we access the data directly from the cloud storage, but there is still some component in the workflow that are not replaced by the cloud. For example, we still request the station response data from the FDSN metadata service. This is part that are not fully replaced by the cloud storage at this moment. And we also see how the document DB, the database server, are reading or are saving our picks efficiently. Because when you scale up, we're writing all of the picks to the same document DB server, and we don't want to mess it up. And at that time, there are like 5 or 6 experiments we made over 4 months, and finally we're happy to say that, hey, we can do 12,000 vCPUs at the same time. Let's do that. And yeah, that's a story about how we scale our workflow and make it to the full quota, and to make the workflow efficient. And yeah, that's a story.
So when you were doing that, did you find like ways to improve the efficiency of the processing, or was it mainly that you found bottlenecks somewhere, like in the file IO, or bugs that you had to fix? Yeah.
Yeah, there are multiple updates. We're keep iterating our workflows, specifically for the cloud platform. For example, there's one instance type, virtual machine types we're using. It's called Spot. It's actually just the idling or unused instance from the cloud platform, and the Amazon are providing them with a pretty much discount, like 90% maximum, and they are really cheap compared to the on-prem instance. But the best thing is that this Spot instance can be called back, can be retrieved at any times over its lifetime, meaning that we should expect interruption when the instance is running on the cloud. So to account for that, we implement a checkpoint mechanism in the database so that when the instance is called back by the cloud platform, a new instance can be launched, a new job can be submitted to continue the previous one that get interrupted. And it turns out that using a spot instance really saves money for on the cloud platform. It's really efficient and cost efficient. And other optimization we made is just let me see, is to minimize what we are writing to the database. There's some funny pricing models on the Amazon, for example. The document DB has two pricing model. One is charged based on how many input and output is being used, and the others is basically charged by its running time. So for our workflow, we are writing the picks at a billion scale, and it really, if we're using the pricing model that charge based on the IO number of IOs, we end up with like thousands of dollars charged. But we noticed that, and we switched to the other pricing model during the 3 days big runtime, and it ended up probably save thousands of dollars for just one single instance. This is kind of the tricky part when using the cloud, and especially when you scale things up, because when you read the documents about how each service are being charged, this seems very small, like 1 millionth of IO charged like $1 or $2. But think about we're doing this same operations at billion scale. It's end up with a lot.
All right, so let's talk about when you ran it. When you ran the whole job and chugged through the whole archive. So what was the runtime like? And the question that everyone has for you, what would the cost end up being like?
So we decided to run the big launch in April 10th or sometimes, I guess. And we started with the latest data in 2025. And we launched 1 year of data for all network code. And we monitoring how the system is working. And we're using like 4,000 vCPUs at a time. And the Earthscope people are checking their S3 storage, the cloud storage, and seeing the request is getting inside and how the system is responding to our request. And we noticed that everything looks pretty good. So we decided to submit jobs for 2024 and 2023. And that's the time we increased the quota to the full 12,000. And it still looks really good. We're happy to see that there's no major pressure and there's no major traffic that's blocking, that's creating bottleneck in the workflow. So after that, we decided to retrospectively submitting data from 2021 and all the way back to 2002. And that's it. That's basically what we're doing over that 3 days period. We submit jobs, check the jobs running status, and surprised to see that 99% of jobs finished in like 1 hour maximum. Some get interrupted because they are spot instance, but they are successfully resubmitted, so the jobs get back on normal. And after 3 days, we check the running job status and find that most of jobs finished and our running queue get back to a quiet state.
And what was your final bill for the project, or how'd the budget work out?
For the PI side, we're charged for like 12,000 for the total run, I think. That's for 1.3 petabytes data from Earthscope, and also we also scan the data from SCDC and NCDC. We are still paying for the database that's being hosted on the Amazon cloud, because we need to keep that database running to provide database query service. And we're also paying for the database itself because it costs some storage, and cloud storage can be very expensive. That's for the PI side. I think there's also some cost on the Earthscope side because this data 1 petabytes of data are saving on the Amazon S3, and it's not going to be a small bill. Yeah.
So was that like when you first decided to try to do this, is that kind of what you estimated that you would need to budget for, or did it surprise you going by the number going up or going down?
I mentioned we did many tests over the 4 months developing period, and over that period, we are also estimate how would the workflow be like, and how would the cost be like if we're scaling the 1 GB or 1 TB small test to 1 PB. We'll keep doing this budget estimating to lower the upper prediction for the total workflow. I remember I was budgeting for like 50,000 during the first test, and after that we implement multiple improvements and optimization to the workflow. Like we merged the I/O from the S3 or write to the database, and there's many updates we made to the workflow, and at the end of the day, before the big launch, we're budgeting for like 25,000 or something. Yeah, it's pretty close to what we are finally charged for this workflow, and still smaller than that. Surprised to find that.
Yeah, well, that never happens. What were the biggest knobs on that? Like what choices drove the cost down, or like what things, if you hadn't optimized it, might have really increased the amount of money that it ended up spending you?
So the first major thing we made is a spot instance. It really saves money, as I mentioned, because when you switch to spot, the virtual machine are charged at a much cheaper price. Now it's still dynamic. Sometimes you get a 10% discount. Sometimes you get 90% discount. Totally depends on the market. But they are much cheaper than having an on-prem instance. The second thing is the optimization on the database. We try our best to avoid making small writes to the database. Instead, we merge them, write one giant data picks to the database at the same time, and we avoid duplicated reads from the database. So it only saves time and saves time for the workflow, and also reduce the pressures we're creating for the database. So it's like reducing the job runtime and reducing usage of any cloud resources, like this minimum things, because it always get accumulated for this giant workflow.
So similarly, the decision to want to push to 12,000 nodes, 12,000 CPUs, do you think, like, was that just because you might as well do it faster because the cost would be the same? Or are you saying that it was actually cheaper than if you had tried to run it on, 1,000?
That's a good question. For the PI team, for us, running the jobs with 1,000 CPUs or 10,000 CPUs, it would probably affect how long we finish the total jobs, right? Yeah. If we can finish scanning 1 PB of data with 12,000 CPUs in 3 days, it also means that if we have only half of the CPUs, we need to elongate the runtime to 6 days. And similarly, the document DB server need to run longer time because it should be keeping in alive through this entire time. But the cost will probably be similar because I mentioned the document DB server is still running, like it's keep running for like 1 month so far because we need to keep it live. We don't turn it off after the workflow ended. But it probably would be a different story for Earthscope because they need to keep the data in an active state, even in the cloud storage. Because once we access the data, this data are being elevated from a sleeping state into active state, which cost more for them. Yeah.
So from your perspective, it was sort of just if we could give us as many CPUs as we're allowed to have, because if we can finish this job in 3 days, that sounds nicer than 2 weeks.
Yes, I totally. I would expect the result definitely faster than slower because I don't want to see the results. Like takes 1 month to finish. And from my perspective, there's no major bottleneck in this workflow that will prevent the current workflow scale to like 20,000, 30,000 vCPUs. But there's need to be some collaborations between PI team and Earthscope team just to make sure that this 30,000 vCPUs is not creating major traffic that blocks the normal operation for the S3 storage. So we never tried that. We don't know, but that's my assumption. Yeah.
It's a fun thing we
Curious
can try
to
to
see.
break next. Yeah.
Yes.
So other takeaways that other people might find interesting. I'm curious, after you finished the main run, did you identify, some more things you're like, ooh, I could have, if we had changed that, it could be even better. Like, did you spot more stuff like that?
Uh, yes, and I think let me say, we noticed some improvements that we should make to the model and to the workflow itself because we're extracting yeah. I noticed that there are some crazily big mini-seed files that really blocks single instance because each of these virtual machines are allocated with 60 gigs of memory, and there's sometimes giant mini-seed file, 900 megabytes, and it's make it really difficult to load with this 16 gigabytes memory instance. And in the next round, we will try to allocate a different instance with much bigger memories for this type of data. Because if the instance is trying to load this 900 megabytes data, it just get out of memory and get stuck as a point. And it seems like the job is running, but it is not. It just gets stuck. And once we notice that, we need to manually stop this type of jobs. And that's the part, kind of the failed jobs I mentioned in the 1% jobs of the 1.1 petabytes of data. And I think this is kind of the lesson I keep learning through this experiment. There's always some improvements that people can make to their workflow so that it really looks like click and run and gives the results.
So I think this might be a difficult question, but I'm going to ask: how much of what you learned to do you think would apply to, pretty directly to like a different kind of analysis to same data, to mini-seed data, or to, maybe a similar machine learning analysis, but with a totally different data type? Like maybe that's an example of, well, if the file, if the like data chunk size is very different, there are some things you're going to have to change. But do you think that you've picked up a lot of stuff that you could now apply in other ways, without having to learn at least all of that over again?
Yeah, I think the key part of having this cloud-based workflow is to have an efficient way to read the data from the cloud-based cloud archive. I think this is the most important infrastructure that will support the scientific workflow that's running on the cloud. And people should understand what data they're running and how the cloud platform can be used efficiently to optimize their storage, their workflow. Because, for example, I'll still take my workflow as an example. If I'm still downloading those data from the cloud storage to a local instance without any change to the current workflow, I was still facing the same problems of having so many storage allocated to each of these virtual machines and load them virtually. So it is important to notice that by leveraging the cloud native packages and load this data directly from the cloud storage, this is a key thing that makes this entire workflow efficient. So generally speaking, if we have an efficient way to load the data and people can adjust and improve and optimize their workflow accordingly, given that they have a full understanding about what their workflow is doing. So I think it is possible, and it is important to know the details in this work through the entire life of the workflow. Input, how they process it, what you are outputting, and knowing these details is important to optimize and leverage the cloud platform.
So probably no one wants to rerun your exact analysis, right? And just do the whole thing over again and reproduce it. But how big is the advantage of, the cloud storage of this data, like the original data sets, for reproducibility or for collaboration, with a larger group, versus if you had to kind of acquire a copy of the data and then try to run it at an HPC? Like, have you thought about things in that way at all?
Yes. So I think we really want to highlight the reproducibility for the cloud, because when people download the data to their local archive, they name it differently, they organize it differently, and they provide different I/O packages that load this data. And when other researchers try to reproduce these studies, they really need to be careful and write the data in the same way to reproduce the study. And but imagine that when we have the mini-seed data, seismic data, or geodesy data sitting publicly in the cloud, and we're basically accessing the same drives. I'm seeing what you are seeing. I'm reading what you are doing. This is the magic, right? And it definitely will greatly improve the reproducibility, because it's basically we're sharing the same drives as you are working on. So I think it's a magic thing for the reproducibility.
Well, I have to assume that anyone who's watching this is interested in doing this kind of thing themselves. So I want to ask for your advice with things you learned through this process, and maybe for different kinds of people. So let's start with people who are a little more used to working in the cloud or things like that. Do you have any advice for someone who kind of understands how this would work now that you've been through it?
So for the people with base cloud experiment, I think it is important to know what you need from the cloud, because most people are using the virtual machines and just going to another place, just like what they're originally doing on their local storage and server. And it's important to know that when you scale things up, where is the bottleneck? Are you still using the FDSM service even when you're on the cloud? It's not a good choice, because basically you are DDoS the Iris web service, Iris FDSM web service. And if you know that you're using the mini-seed files on the cloud, then go to the SDDC, go to the NCDC, and potentially go to the Earthscope. then that's a leap from the FDSN web service to the cloud native version. Yeah, I think, and when people are saving their results, for example, the phase picks or course correlation functions, if someone is doing the ambient noise study, uh, are you still writing this course correlation function locally and write it or download it to your laptop for further process? Because the S3 storage is right over there, and you can write it directly from your virtual machines as the output. That's also the gap between running on the cloud and being cloud native. I think that's an important concept, and people can learn to improve their workflow. And I really like the idea about being cloud native. It's a really efficient way.
What about for people who really have no experience working with the cloud? So if you can try to remember what it was like before you were, one of our cloud experts, is there advice you would give someone who's kind of thinking like, that sounds cool, but I don't know where to start with that?
Yeah, I think it is important to find the right educational materials or tutorials to get started up with, because playing with the cloud platform from the 100 version or something really takes a lot of time learning a lot of the details, especially this each of this cloud platform usually have their own terms that before getting onto the cloud, you don't really know what is what the product is about. Even with so many times working on the Amazon cloud, there are still so many advanced service, high level service that I have no experience so far. So it is important to find the reference education or tutorials that get you up to the cloud. And yeah, I think once you get up there, you're basically following the same procedure, like building the experience, knowing your workflow, and knowing the details, and try to learn to be efficient like cloud native. Yeah.
All right, one last question for you then. If you don't mind sharing, what's the next step for you on this project? What are you doing now that the catalog exists?
I think we're currently collaborating with the community to looking at specific site, not globally, but for example, the West Coast. We're actively putting the data that each of these research groups are interested in, and we are providing this picks for them so that we can collaboratively working for a large scale earthquake catalog. So this is going to be a really precious database for the community who study the earthquake catalog that has a station covered by stations, and also similar data to the earthscope.
Great. We could keep doing this for a while, but I promised I would let you go at some point, so I'll do that now.
Okay.
So thanks very much for your time and for being open to share this with everyone, Yiyu.
Sounds good. I like this experience. It's really fun.
Great. So if you're watching this and you're amped up to try something similar, come and talk to us at Earthscope. We built some railroad track ahead of DataMine, and your project might require a different railroad track, right? So we're not quite at the self-serve point yet where we don't have a full set of documentation. So you're going to need some direct support from us. And there also might be helpful opportunities we can point out for you, like the AWS Open Data Program that we're currently working on might make some of this easier for you. But bring us your ideas. We're eager to see more of these projects. We want to support more stuff like this. And finally, as a reminder, you can find all the information and updates related to this Cloud On-Ramp project to help researchers get into cloud computing on our website at earthscope.org/data/cloud. So for now, thanks again to you, and thanks everyone for watching.